Got it.
Okay, I'm not sure why that, okay.
All right. Well, welcome back, everybody, for the third in our distinguished alumni series, celebrating our 100th anniversary as a department. Today, we're pleased to welcome Tony Remijan, who was a graduate student here and with Lou Snyder, got his PhD in 2003, working on biologically important molecules in the interstellar medium and in comets. I assume that was with Karma. And
no, it was with BIMA.
Oh, okay. That's right. That's right. Karma came. Yeah. Okay. Good.
Yeah.
With BIMA. Wow. And since 2008, he's been at NRAO in Charlottesville, working with ALMA, and is now the manager for the North American. His LinkedIn shows a North American ALMA Research Center. But
that's wrong.
Okay, so you got to update
North American ALMA Science Center.
Okay, so probably can tell you everything you want to know about using the world's largest radio telescope. And so today he's going to tell us about molecular cores and comets and prebiotic molecular complexity in astronomical environments. So take it away, Tony.
All right, thank you, Paul. Thank you for the introduction. They wanted me to say something about Illinois and my time at Illinois, and I think the best thing I could do there is just go ahead and start into my talk, because I will, the first part of my talk is going to be discussing the original detection of interstellar formaldehyde, and that was done by, of course, Lou Snyder back in 1969. And so as I go through my presentation here, I'll talk a lot about Lou and the impact that he has had on myself, my research that I've been doing, and then hopefully continuing on with the research that I am passing along to the graduate students and postdocs that have been working with me for the better part of the last 10 years. So that's, I think, is the best way I could, show my appreciation for everything that Illinois offered when I was there. So we'll talk about the detection of formaldehyde and starting at the beginning, for the start of astrochemistry. Then we'll move more to more complex molecules and the interstellar mapping campaigns that we have done over the course of the last several years and in the last decade on things like acetic acid, acetone, and some of the larger C2H4O2 isomers. And then Leslie wanted me to talk a little bit about how that connects to planetary systems. And the overall theme of the presentation is how we're going to use the interferometric maps of these large molecules to understand something more about astrochemistry and the formation of large molecules in space. So we'll try to make this connection between the interstellar detections that we've had and what we have learned there from looking at the maps we're making of some of these large molecules, and how that connects to the maps that we made of large molecules in comets, and to understand their chemistry. And then finally, in the last couple slides, last few minutes, we'll talk about the limits that we have on molecular complexity. And there's a great plot that was made for the NGVLA at low frequencies at Q-band from 40 to 45 gigahertz on some of the molecules that may actually be detected when the NGVLA comes online. So we'll break it up to talking about 4 parts. First, starting with the detection of formaldehyde, going to our complex molecule mapping in the interstellar medium, as well as in comets, and then talk a little bit about the limits, molecular complexity, and what we actually need from chemical models. So just to put everyone, what I want everyone to have here for the course of the next 45 minutes or so is let's have a little fun and let's reminisce and pay our respects to Lou Snyder. He was a pioneer of this field. He had a great impact on myself and on my family, and I'm really happy to continue the science that he started almost 50 years ago now. I want to give everyone an appreciation that, astrochemistry has been around for the better part of 50 years, but we still don't have a very good understanding of interstellar chemical processes. We don't have that theoretical basis that physics has in general relativity, that we could go out and test general relativity or even special relativity in astronomical systems and get the right answer. We don't have that yet in chemistry. But what I'm going to propose is that using a combination of chemical mapping, high resolution spectroscopy, and high resolution imaging with modern interferometries, we can start answering the question of how are large molecules form in space. And for some of you that may be on this call, you know how much I hate this picture, this image that I made from a press release about a decade ago. but it really summarizes everything that in the interstellar life cycle of forming molecules, how molecules are formed from, mass loss of stars, getting into diffuse clouds, forming planetary systems, getting that chemistry bottled up into comets and and asteroids, and then getting onto stellar systems by impacts. So those are the goals of today. Above all else, have a little fun. We're doing astronomy and astrochemistry. This is fun stuff that we do. And let's take a break for the next half hour, 45 minutes, and have a little fun with astrochemistry. So let's start at the beginning and the detection of formaldehyde. So really in 1969, there was an observation that was made at the NREO Green Bank 140-foot telescope that changed the way that astronomers and chemists view the universe. And this was the detection and absorption of the fundamental transition of formaldehyde at around 4.6 gigahertz. And this publication was actually in Physical Review Letters. This wasn't in APJ or anything like that, but that was the importance of this detection, because up until this time, it was widely well known that you could not form molecules in space. That is just something that is not done. Space is, the conditions of space are too harsh to actually form molecules. You're not going to actually have the right conditions to form molecules in space. So this is a waste of time to actually look for molecules. And even the detections that were done of diatomic molecules like CH, CH plus, or CN that were done in the optical, infrared, and UV part of the spectra, they were really not considered as viable candidates for molecules. Here's an excerpt on these identified interstellar lines that said, hey, look, these are very improbable to be interpreted as molecular bands. So from about the 30s to the 60s, not a whole lot was done or even talked about in interstellar chemistry until OH was detected in 1963 in absorption. Here's the beautiful spectrum that you see, an absorption line feature of OH. And the lighter gray line is basically the off position to show that there really is an absorption feature here of OH. So for 30 years, you were only seeing diatomic molecules found in space. They were very simple hydrides that contain one heavy atom and hydrogen, and that was pretty much it. Until Lou came along. Now, Lou came along in 1967 at NREL, and he was going to work with a fellow colleague, Dave Buell, who was actually an electrical engineer, and they were a fellow molecule hunter, and they were discussing the probability of actually finding water in space. So they had done a lot of calculations on the probability of actually looking for transitions of water in space, and they were going to present this, and Lou had a talk ready to go at the Austin meeting in 1968, AAS meeting. And he gets up and starts his presentation, and was going to start his presentation. But before that, Charlie Towns stands up and announces that in the middle of the presentation, before even Lou had a chance to talk, that his group had discovered ammonia in space with the Hatcrete Millimeter Observatory, the Hatcrete Millimeter Wave Antenna. And here is that detection. Now, but the fun part of this is that here is the line that was detected at that time in the late 60s. Here's the ammonia line and all the hyperfine components. And this top shows how many hours of integration time was needed to get those points across that line. So two and a half hours here in these 4 points, about 5.5, over 6 hours of these points over the middle of the line. This just shows you the amount of integration time that was needed just to get this line of ammonia at that time. And here's the off position, about 3 hours in the off position. They also looked for the J2, K2 transition inversion line of ammonia, but they didn't actually see it. But this is what's, before Lou ever had a chance to give his presentation on the possibility of finding water in space, Charlie Towns got up and showed his detection of ammonia. So he had now ammonia. A couple years later, water was detected and it was actually turned out to be a source of maser emission. So it was really time to get serious about searching for larger molecules. Now that we had these, they were still large in the sense that they had multiple hydrogen atoms, connected to a single heavy atom. But the idea was that NREO facilities would be well positioned to lead these searches. And one of the spectroscopists working with Lou was Rick Sinram, doing a lot of detections of these molecules in the laboratory, and then to try to go search for them with NREL facilities. And they had a lot of molecules they wanted to look for. Formaldehyde was just one of them. But you had formaldehyde and water and ammonia and a lot of these other molecules that were being characterized in the lab that they wanted to actually search for with NREO facilities. So Bill Howard was the assistant director of NREO at the time. They talked with Lou and with Dave and with Rick, and they said, okay, just write down all the molecules you want to search for, and then submit them to kind of in a special call to the director, kind of a DDT, to whatever molecules you wanted to look for and how much observing time you think you need. But the director at the time wasn't very enthusiastic. It was going to take months of observation on the 140 foot, and then over a year or so observing on the new 36 foot out in Tucson. But they did what they were told. They submitted a proposal to Dave Heshin, and as I said, Dave Heshin was not too excited about this proposal. As a matter of fact, in the review of the proposal that was sent back to Lou and his colleagues, says something to the effect of how irresponsibly the PI is acting, requesting months of this time on the 140 foot, and almost a year on the 36 foot. What exactly were you trying to do? I also know a couple of people around this call that are part of the new distributed peer review of ALMA. And if you've got this kind of review, it may not meet the criteria of a, let's say a useful review that would be sent to the PI. This is, back in the day, distributed peer review was not something that was thought about. But this is the kind of response they got from the director of NREO at the time. And diplomatically, Dave Buell says something like, we're trying to get people interested in molecules in space, with a very scathing response, well, you have failed to interest me. Now, those of you that did know Lou and knew Lou well, he had a much more colorful response that he replied to the director of NREO at the time, but I'm not going to actually repeat those words. But the idea was this was going on without NREO involvement, and it was something that we really needed to get into if we were going to compete with the new facilities coming online and searching for molecules. So after a lot of cajoling, okay, Lou and Bill Howard decided to, okay, you could search for these molecules, but you had to get agreement from other programs that were already approved on these telescopes in order to search for the molecules. So there was there was no dedicated program to search for these molecules in space. But if you found another program that was searching for or doing other type of science that you could put in the frequencies that you wanted to search for, then you could piggyback basically on that proposal. So they negotiated a deal with Ben Zuckerman and Pat Palmer, who had time looking for OH sources. So we already knew OH was detected years ago, and so they worked out a scheme so they, in addition to the OH observations, they could also put in transitions of formaldehyde. So that's why the original detection paper had not only Lou Snyder and Dave Buell, but also Ben Zuckerman and Pat Palmer, because it was actually their already approved time on the telescope to search for OH that they piggybacked on in order to get the formaldehyde detections. And then finally in the spring of 1969, after all this cajoling and back and forth, they finally found the transition of formaldehyde. And there it is in all of its glory on the left. This is the original detection paper that shows it was toward the Sag-A region, and it shows a nice absorption profile. And it turns out all these other absorption dips that are in the spectrum were actually from line of sight clouds between us and the galactic center. And just for fun, here is a similar looking spectrum on the GBT that was taken as part of our GBT Primos Large Survey. This was toward a different source, SAG-B2 North, not Sag-A, but it clearly shows the line of sight clouds along from us toward the galactic center, showing all the absorption features due to formaldehyde. This was taken, of course, in several hours. This is in 1 minute of integration times on the GBT. You get this beautiful spectrum. So this line, the rest is history after that. Line was observed in all these different sources across the sky, and then actually 13 CO was detected. The 13 isotope of CO was detected later in the following year as well. So this is the story of how Lou actually was able to get on the telescope to detect formaldehyde and created what we would say the modern astrochemistry that we are still doing today. That's the first part of my talk to kind of give you an idea of where we are in terms of how we got here as a science, starting from the first detection of formaldehyde. So I guess I could ask Paul if there's any questions about this first part before I can move on to the second part of my talk about mapping campaigns and using BIMA.
We can pause for a moment. If Anybody who wants can raise their hand. Not seeing anything. Why don't you go on?
Okay. So moving on to the second part now is, we have the detection of formaldehyde, and there you have formaldehyde. You have the CO molecule and two hydrogens attached to it. So as we were moving into the 70s, out of the 60s into the 70s and 80s, we started to look for more complex molecules, and then eventually onto mapping these molecules toward these sources. Now, the molecule that everyone wanted to go after looked pretty similar to formaldehyde. If you squint light a bit long enough, there's your CO. But instead of a hydrogen here, you would attach, an OH molecule, and instead of a hydrogen on the other side, you attach a NH2CH2 molecule, and you get something called glycine. Okay, and you get glycine in a bottle now. It's a supplement you could buy at any vitamin store. But interstellar glycine was really hot to search for because it would be the first detected amino acid in space. And so they started to characterize the spectrum in the late 70s to search for interstellar glycine. And you can see Snyder and Hollis and Lovis and Sinram were going after this, the lowest energy conformers or higher energy conformers of glycine, both with the 140-foot telescope. They searched for it with the 12-meter telescope out in Arizona, then actually do a search for it with the VLA as well. I would love to say that this proved very fruitful, and glycine was discovered very shortly afterwards, but nothing was found. No glycine was ever detected, and to this date, no gas phase detection of interstellar glycine has ever been verified and confirmed in the interstellar medium. It's been observed in the Murchison meteorite. It's been observed in comets, but no gas phase detection of glycine has been detected. Just looking at interstellar clouds, so we're still curious as why that is, but we could talk about that later if anyone has questions about it. So no glycine was found, but during these initial searches and basically building up more and more spectra from these sources, a lot of other molecules were detected. Things like formic acid, that is the primary acid you find in bee stings, methylformate, dimethyl ether, large cyanides. Here's an example of an Orion spectrum that was taken where they were looking for transitions. Here in the K5 line here is where they were looking for glycine. You can see nothing there, but two very strong lines of methylformate were detected in these searches. So we're starting to build up an inventory of molecules, complex molecules in the 70s and 80s. We weren't finding glycine, but we were finding a lot of molecules that were pretty complex. And as receivers got better, as telescopes got better, the search intensified. Not only were we covering more bandwidth, we were covering more sources, we were covering, we were building better instrumentation. All we were looking at, though, when we were searching for glycine was just a wall of lines and interspersed with a lot of blank spectra. So there was no glycine that was detected in any of these sources, but we were finding a lot of other molecules. And Lou came to the realization that perhaps we were not using the right facility, we were not using the right instrument in order to search for these larger molecules. We were finding a lot of big molecules, but not things like glycine, not things like the large acids. So he wrote the paper in 1997 that said that the way that we're going to start looking for molecules was to use millimeter arrays. So the reason why we were not detecting these large molecules like glycine was because they were beam diluted. So we had this large single dish beam that was pointing at one of these sources, but all the emission was coming from very compact sources called hot cores, where a lot of the chemistry was taking place, not in the gas phase, but on grain surfaces. And this chemistry that was happening on grain surfaces would then be released into the gas phase by, let's say, a newly forming protostar, but we weren't going to be able to detect them in the outer regions of these envelopes. We had to look at the very small hot regions inside of these large clouds. And the only way to effectively do that was to look at it with an interferometer, because we couldn't build a telescope big enough to get to the resolution we needed to really pinpoint on those hot cores that we were looking for. And for a while, seemed like Lou's argument was actually correct. So, shortly after this was published and people started building the ALMA telescope, BIMA was, working just fine, and they started pointing BIMA at, these iconic sources, the Galactic Center or Orion. And they were searching for these complex acids and large molecules like acetic acid. And the first detection, and I would argue to this day, there's been no detection of acetic acid with a single dish telescope. It has only been made with interferometers. But this was the original detection paper in 1997. And the background continuum that you see in grayscale here is a centimeter wave continuum observation, about 6 gigahertz. And the contours are where the emission from these transitions of acetic acid, this one here and this one here, are coming from. So acetic acid are these points that are highlighted kind of in the middle of the pass band. So we were finding compact emission of acetic acid with using both the BIMA array and the Owens Valley array toward these sources like the Galactic Center, SADP2, the LMH. So, okay, we could actually do this now. Using these kind of arrays, we are now searching for molecules and finding these large organic molecules in these sources. Can we actually now do any chemistry, knowing that we have not only the spectrum, we could identify the molecule, but also we could identify where is it coming from in these sources. So I did a large survey of acetic acid toward a lot of molecular cores. We found it in SADP2, we found it in W51, we found it in G34. Here is the detection, which as young graduate students are looking at this is a fabulous detection that took dozens and dozens of hours on BIMA to find these lines. But I found 8 lines here of acetic acid. They're all lined up very nicely when you put them a dashed line through it. And then what I did was I mapped the distribution of acetic acid here in the dark contours from this line right here and this line down here on top of methylformate. So methylformate is a similar type of molecule to acetic acid, has the same constituent atoms, but they're organized differently. So methylformate, if you could see that on your screen, has this configuration, whereas the acetic acid has this configuration. Same atoms, they're just configured in a different way. And here are the 2 lines of methylformate that were detected. Methylformate was easily detected, been well known since the 70s. Acetic acid wasn't detected until 1997. But you can see in this low resolution blob kind of emission, we were seeing that the methylformate and acetic acid were showing up in about the same regions toward this source W51. We also did a big survey and found that most of the acetic acid sources were within about 7 kiloparsecs of the galactic center. So this is kind of telling us something possibly about the chemistry that's going on in the galaxy, that maybe only the large molecules can be found kind of closer in to the galactic center. Once you get further out into the galaxy, maybe the metallicity is decreasing. We know that is the case. Maybe it's not driving interstellar chemistry to these large molecules out further than about 7 or 8 kiloparsecs. So these are the type of studies that we were able to do at the time to actually think about, okay, where the molecules being found, in what sources, and about where they're at in the galaxy. Not only were we looking at like this molecules like acetic acid, but we went back and also looking at the BIMA array, looking at the distribution of comparing different types of molecules like acetic acid, methylformate, but then we also started looking at formic acid. Formic acid is a little bit simpler. Instead of having a methyl group there, CH3COOH, it just has HCOOH. It's a little bit simpler. And we were able to detect it in Orion in the compact ridge region. Okay, so here's all the transitions of the acetic acid that we found toward the compact ridge. And this is a continuum image again in grayscale with the formic acid now plotted in the contours. And we detected in the compact ridge of Orion, but not in the hot core. Now, this is going to be important later. There will be a test on this, but the formic acid is detected in the compact ridge, not the hot core. We also detected, this in W51 as well. But we're going to focus on the formic acid distribution in Orion going forward here over the next couple of slides. Remember, it's in the compact ridge, not the high core. So BIMA was doing pretty good. We see some of these molecules, but we still wanted to get higher resolution. And as we got higher resolution going toward things like KARMA or the Plateau de Bureau or even EVLA, we were able to not only map these large molecules, but their distributions and their morphologies turned out to not be the same. So when we were able to get to higher and higher resolution, we were not just finding blobs anymore, but we were finding the actual morphology of these molecules in these sources. So this is a Plateau de Bureau map done at pretty high resolution of a couple molecules. This is methylformate again. It's kind of showing up here, ABC. We see that ethanol, another molecule, showing up in region B. Okay, and this is the line that is being mapped. Dimethyl ether, another large molecule, showing up again, kind of A, B, and C. So all these molecules with oxygen are kind of showing up in the same spot. We can at least see them in the same sources, but the molecules that had nitrogen in it, okay, were showing up in this region D up here that they identified in this survey. So the oxygen molecules were kind of showing up in one spot. The nitrogen molecules are showing up in another spot in these little bit higher resolution observations that were done with the plateau. So we're trying to now tease out some chemistry. Now the nitrogen molecules and the oxygen molecules aren't showing up in the same spot. Maybe that's telling us something about the chemistry. So the molecules now were showing up in different regions. They did not have the same morphology. Great, so we could start following on these observations with even more complex molecules. And well, that's strange. Not all molecules were showing up where they were supposed to be. I said that, the oxygen molecules were showing up in one spot. The nitrogen molecules were showing up in another spot in Orion. Well, here's a nice oxygen-bearing molecule. It's called acetone. If you have nail polish remover, that's what acetone is. So, you have acetone here showing up toward the hot core. And remember, dimethyl ether was showing toward the compact ridge where formic acid was. All the oxygen molecules should be showing up toward the compact ridge. What is acetone? A molecule that has no nitrogen in it showing up in this core, kind of to the northwest there. So that was very strange. We needed, as we're going over to now higher and higher resolution, we started, at this time, ALMA starts to come online, and we start to use the ALMA science verification data to investigate some of these molecules at high sensitivity and high resolution. Up until this point, we've had the plateau, we've had KARMA, we've had BIMA, but really ALMA started turned on, and we can actually start looking at some of these sources with ALMA. And this is what we found. This is a very messed up this is a very messed up map. I'm going to walk you through it a little bit, but here's the methylformate in blue. The methylformate is toward that compact ridge region. It was where the oxygen molecules are supposed to be showing up down here to the south. The red contours are the ethyl cyanide. It's a large cyanide molecule. Those are showing up more to the northwest. This is where we expected the nitrogen molecules to show up. Acetone, which has no nitrogen, it's a big oxygen atom, and a structurally similar molecule, dimethyl ether, also shows up toward the compact ridge. Acetone is showing up somewhere in the middle and more toward the nitrogen core, let's say, in Orion. So now we had molecules that weren't even following what they were supposed to do. This has led us to an idea that there is something going on with the chemistry. Maybe the formation of acetone is dependent more, not on oxygen chemistry, but involves some type of nitrogen chemistry in order to drive its formation. This is a possibility now that we have the chemical maps, now that we have the maps of these molecules in these regions. So it's possible that these large molecules and the maps of these large molecules are telling us something about the chemistry. Now, this next slide I'm going to show you is another big mess, but it's really cool. Look at this paper if you get a chance, because we actually made a 3D model and rendering of the Orion cloud and all these different molecules. So I don't expect you to get anything out of this except for sort of a pretty picture, but we mapped the cyanide, the acetone, and dimethyl ether in 3 dimensions, and you could actually download the data, and you can kind of look at it in 3 dimensions to see where it is in the cloud. So that's the only reason why I show this slide, is because there's a really cool way to actually visualize the acetone distribution in 3 dimensions. So can we now, once we have the spatial distribution of the molecules, can that tell us something about the interstellar reactions that are going on? So this leads to a follow-up, one other paper before we move on to the ALMA observations, where we looked at specifically the formation of methylformate, okay, heading down here to the compact ridge, but then formic acid. Okay, we're speaking a lot about formic acid and methylformate. The methylformate here is in the blue contours. The formic acid is in the black contours. And it seems as though the methylformate is kind of digging out a hole of formic acid, or the formic acid may be forming at the expense of the methylformate. And even at high resolution, you see the same thing. These are KARMA observations, high resolution observations of the methylformate knots around these cores, but it really avoids the formic acid. Whereas if you look at methylformate and dimethyl ether, they're almost exactly right on top of each other. So we're starting now to say, okay, does the spatial distribution of these molecules tell us something about the chemistry? That's the question that we're trying to go after here. So this is a very new field, and there was only one other reported study that said that the gas phase distributions of methylformate, formic acid, dimethyl ether, methanol are highly correlated, okay, that may tell us something about their formation chemistry. And what we proposed in this paper was that the reduction of formic acid at the methylformate peak shows us there could be a correlation in how this molecule is formed from methyl, basically, are we forming methylformate from formic acid? So this is where, we really started to look at seriously, can the spatial distribution of molecules tell us something about the interstellar chemistry that's going on and reactions that are taking place in space? So ALMA was coming online. It was a great time. We had this ALMA science verification data. So this is going to open up a brand new field of actually looking at the spatial distributions and interstellar reaction processes. And this is what we got. ALMA turns on. This is the spectrum of Orion that you get in one 45-minute observation. Now, just to give you an idea of how much data that are contained in this one slide, this is more data at the time that was collected on Orion interferometrically in 30 gigahertz of bandwidth than had ever been collected interferometrically on Orion ever in all the history of radio astronomy. So this 45-minute observation collected more data on Orion interferometrically than had ever been collected before. And people are still using these set of data in order to try to disentangle the chemistry that is actually going on in Orion. We found, so this is what we're dealing with. That is exactly what we're dealing with when we look at spectra from ALMA. And we started to map new molecules. So there was a couple of detections that came out, and we see that, we're detecting new molecules. This is N-propyl cyanide toward the galactic center, and we see its distribution again. Okay, we could actually now get higher spatial resolution observations. We got beautiful spectra. Moving on, this is a paper that we did a couple of years ago on the first interstellar detection of methoxymethanol. Kind of a big molecule here. It's related to methanol. All the lines that you see in red are the detections of the methoxymethanol methoxymethanol molecule. Here's a bunch of different maps that we show on different energy levels. These are all transitions that we map of methoxymethanol toward this one source. This is a source called NGC 6334I. And we compare the distributions of methoxymethanol to other molecules like ethylene glycol or methyl cyanide or even methanol. But this is now actually done pretty routine with ALMA. Those hours and hours and hours of BIMA observations just to get that one tiny little blob of acetic acid. I was very proud of that back in 2003. This is now routine. Acetic acid is now found in a lot of different sources interferometrically. Here's the same source, NGC 6334I, mapping the distribution of methylformate again. Beautiful images. Acetic acid, glycoaldehyde, all these structural isomers that are telling us something about where these molecules are formed. And not only regular acetic acid, but higher vibrational states of acetic acid are now being detected. So this is the early days of acetic acid. They were trying very hard to actually find that one. I was trying very hard to find that one particular transition. Now, not only can you find all the ground state transitions, but you can find all the excited states of all the vibrationally excited states of acetic acid. Again, mapping all different types of transitions of this molecule toward this source, NGC 6334I. And this is work that was done by my graduate student, Cece, who's in the audience today. But, just something that was done, took painstaking amount of time back in 2001, 2002 is now almost trivial to do with ALMA here nearly 20 years later. Now, before I move on, I'm going to stop for a second. I've been talking for another 15, 20 minutes and see if there's any questions before I talk about, can we understand more about the chemistry that's going on in these regions?
Go ahead, Brian.
Yeah, so hey, Tony.
Hey.
So you've been talking about all that you get to learn from the spatial distribution. So how about from the intensity? Can you say anything about the different masses of the different components and what that might say about the chemistry, or is that is that not possible? Are they too optically thick for that?
Well, some of these transitions are they are optically thick. I don't have a slide showing that, but some of these transitions are actually optically thick. So the lines are kind of cut off due to the optical depth effects. The relative intensity, what that gives us, if you can measure the relative intensity of all the lines that are in the source, you're going to be able to get an estimate of the temperature of the rotational temperature of that molecule within that source, and also its abundance. So we use the intensities of the lines in order to tell us something about the physical conditions and physical environment of that source. And you're right, some of them are optically thick, but some of these transitions of things like vibration excited acetic acid, they're nice and optically thin, and they're well characterized by, let's say, an LTE approximation. But can we tell anything about the chemistry of that? The next set of slides are going to try to explain how we could actually try to disentangle the chemistry by looking at the transitions of the molecules. Because right now, all we've been really able to do is look at particular transitions of molecules in these sources. What we really want to do is find where is the molecule chemically in that source, not just a particular transition of that molecule. So we can find out more about the physics, physical conditions, temperature and density in those sources by looking at the relative intensities of all the lines.
Got it, thanks.
Tony, I have a similar question. Actually, what can we learn from the velocities?
From the velocities, and if you look at this paper, there's more plots in here that actually show the kinematics of this source and what we think is going on there. But from the velocity components and the velocity dispersion, you could look at more of the kinematics of what's going on in these sources. When I get to the comets, I'll show you, the line profiles that show different structures of the lines that actually will show what we think is going on in the coma of comets by looking at not only the maps of where the molecular emission is coming from, but also the line profiles and where they're showing up. Also the line profiles. Sorry, just leave it at that.
Okay, cool, thanks. I don't see any other questions. Why don't we go ahead?
All right, let's keep moving. And that's a great question that Brian asked, because it talked about, what can we get from just looking at the individual transitions? What we really want to do, because we have individual transitions, maybe we're just looking at high temperature gas by a particular transition. Maybe we're just looking at high density gas because of the critical density of a particular transition. What if we wanted to look at the overall molecular emission, not just from a particular transition of a molecule, but look at all the transitions of a molecule and see if we could get the real molecular emission from the entire ensemble. And this is what Cece did in this paper when she looked at all the different transitions of a particular molecule that we could, in a particular passband, and then put them on top of each other. So I'll try to I will try to do my best here to explain what she did in this paper about moving from a transition map, things that we're used to seeing, to what we are now calling an actual chemical map of the source. So the black spectra are all the transitions that are coming from all the molecules. This is your astronomical spectrum. The blue dash, I'm sorry, not blue, but the green dashed lines are our model of a particular molecule. In this case, it's methylformate. And you can see that some lines are well characterized than others, better characterized than others. Here's a line down here that seems to be very well characterized. This one as well, the line intensity matches what we see in the astronomical spectrum. But if you look over here, this modeled line is buried underneath another stronger feature. Okay, but the utility is to look at every one of these transitions and look at their morphologies and distributions and see what it looks like. So that's the next slide. The next slide looks at every single one of those transitions and what its morphology and distribution looks like. And that's regardless of energy, regardless of the upper state temperature. And you can see that most of it they're very consistent across all of the maps. No matter what the transition is and what the energy level is, a lot of the maps look very consistent. Some of the maps are higher signal to noise than others. That's to be expected because weak lines may be a little noisier. So this is how we could tell, maybe, by looking at their morphology, looking at the distribution, if a transition is really contaminated by some other feature. So that was methylformate. Let's look at glycolaldehyde. again, we can look at all the transitions of glycolaldehyde. These are the clean transitions that CC pointed out, that CC found. And you can see some very well characterized transitions, very nicely match the model. But again, you have one transition here that's completely buried under another transition. So we're only going to focus on imaging this particular transition that looks clean. And how does that look transition by transition? You can see that for most of the transitions that we see, their morphology and distributions are largely the same, but every once in a while you have an outlier. Okay, so this could be either, we talk about, Paul, you asked a question about, can we tell us something about line profiles or kinematics? It could be another velocity component of that transition of that particular molecule, or it could be another molecule altogether. But when you put the ensemble of all the transitions all together, put them all together on a single map, you can now really differentiate between the spatial distributions of the different molecules. So this is what all the molecules, all the transitions of methylformate look like in that entire passband. Here are all the transitions of the molecule glycolaldehyde and what it looks like. And what we have shown is a primary component in the solid lines of 64 kilometers per second. That's where most of the emissions showing up, and another component up here at a different velocity in the dash lines. But you can see that the distribution of the molecules, we kind of focus on where all the X's are. Okay, they're different. The methylformate has a completely different morphology than glycolaldehyde, and glycolaldehyde and acetic acid kind of look about the same. But can this tell us now that we're able to take the physics out of it, now we're able to take out, well, this is just a high energy line tracing high temperature gas, or this is a high, this transition is tracing a high density region. We've taken all that out. Now we could focus on a chemical map, and we could disentangle physics from the chemistry. So these chemical maps will tell us something about the chemistry. We're beginning to see really now the utility of using this to determine the formation chemistry. It tells us something about how these molecules may be formed by looking at the different distributions of molecules. One molecule is formed at the expense of another one. Maybe that's telling us about the chemistry. We see a very heavy oxygen molecule in a region where there's a lot of nitrogen. Maybe that's telling us something that molecule is formed, that oxygen molecule may need some type of nitrogen chemistry in order to get it going. So we see that the isomers, the molecules that are of the same family, that have the same atoms, only arranged differently, they show up in different morphology as well, different spatial extent. That's telling us each one of them has an independent formation chemistry, and they're not related to one another. So we are now starting to see how these chemical maps tell us something about the formation chemistry, could tell us something about the formation chemistry of these molecules. Yet the spatial extent and morphology of molecules are not taken into consideration in chemical models. The chemical models are very reactive and not predictive. More on that later when we get to the end. But it's really showing the power of arrays to demonstrate possible chemical formation pathways for some of these molecules. And this is what we've been doing now for the better part of 10 years. And we apply it not only to interstellar clouds, but also to things in our own solar system like comets. Okay, so how can we get this idea of mapping, molecules in comets? Could that tell us something about the chemistry that's going on in these regions? And typically what you would do is, historically, you'd start at the beginning where single dish observations dominated detection of molecules toward comets. And there really wasn't a whole lot to detect until 1997 came along. There was a lot of detections of OH. There was a few detections of ammonia, a couple of detections of formaldehyde. But with Comet Hale-Bopp that came about in 1987, this showed just the true diversity of molecules that were found in Comet Hale-Bopp. The first time I actually saw Comet Hale-Bopp was in my rearview mirror driving. That's how bright this thing was in the sky. So it was really incredible comet that came by, and there was all kinds of single dish observations and interferometric observations that were targeted toward Hale-Bopp to try to really see what kind of chemistry was going on. So you have molecules like HNCO, and you have formamide. Here's formic acid again. And this is what they did here for methylformate. They stacked a whole bunch of lines on top of each other and got an early detection of methylformate. Now, Paul, you're asking about the morphology. You could see all the different types of line profiles from each one of these different molecules. That's going to be telling us something about where these molecules are in the cometary coma and how they're moved around. One of the big detections was the detection of ethylene glycol in this comet. So here's a couple of lines of ethylene glycol in comet Hale-Bopp. So, really the comet Hale-Bopp, uncovered, this was the comet to go after, and a huge molecular complexity was found in comet Hale-Bopp. But it took the comet of the century to really have us detect molecules with arrays. I did some work on this. I did some methanol observations of comet Hale-Bopp with BIMA, and I was able to, characterize comet Hale-Bopp. I could find, going back to Brian's question about what we could get from the line intensities, by modeling, the coma, I could get a very good temperature. I could tell you how much of methanol was in the coma. So the blue line, the blue trace is my model of the comet Hale-Bopp coma and its temperature. And you can see that, over, these 5 transitions, the temperature and column density was well characterized. I could then tell you about the distribution of methanol in the coma. It was very spherically symmetric and kind of, a very nice outgassing out from the coma. This is the model that I used in order to subtract away what I actually observed, and basically you just see nothing but noise. So molecules like methanol were very well behaved in the comet Hale-Bopp. They were coming right off the nucleus. They showed a distribution very spherically symmetric out to a certain scale length, and then they were photo-dissociated. And we use this information from arrays to find not only distributions of methanol, but also a new photo-dissociation scale length for carbon, for CS. And also a large mosaic was done of HCO plus and showed the distribution of that molecule in the coma, not only in the coma, but also in the ion tail as well. So we are able now to use the maps, and we could actually model the distribution of these molecules to understand something about the physical conditions and what's going on with the methanol and some of these other molecules in the coma using the arrays. This is, again, going back to, now this is BIMA observations of comet Hale-Bopp of formaldehyde. And formaldehyde, the BIMA models are these 2 little blobs that I see right here. There's the 2 little blobs. There was a spectrum. It was a very, very thin line because of the resolution we had with BIMA at the time. But we compared that directly to the observations that were done at the 12 meter at the time. And the 12 meter map, they actually mapped the large scale distribution of formaldehyde in this source. And the conclusion from this paper that we wrote was that it was possible that the formaldehyde showed enhanced production in the outer coma, and maybe due to the photodissociation of methanol. And really, until this point, all we had was a single dish observation of methanol or a single dish observation of formaldehyde that was trying to tell us something about the distribution and abundance of these molecules, but we couldn't really talk about its formation. Until we were actually compared the interferometric observations with a single dish observation to show that, yeah, there really is an enhanced abundance of formaldehyde in the outer regions of the coma. So, but we needed the comet of the century to do this until ALMA came along. And now ALMA comes along, and you can do this now routinely. So with any comet that comes by at any time of the year, you can do the exact same thing. And these maps may not look that great, but they're not on comet Hale-Bopp. These are just kind of run-of-the-mill comets. They're you can hardly see them in the sky, but you can now do this type of chemistry investigation by looking at, just relatively, you don't need a big bright comet to do it. You could do this now with ALMA with pretty much any comet that comes into the solar system. So these are observations that we did of comet Lemon and comet Ison, showing the distribution of HCN. This is HCN, this is HNC, much different distribution, is kind of all over the place. The blue and the red is the continuum observations. Again, really with ALMA, this is the first time we were able to get a really good measure of the continuum observations of comets. We were not able to do this before. And then here's our formaldehyde again. The formaldehyde, was much more spherically symmetric than we thought in Ison, but at comet Lemon, you have these kind of weird lobes that are coming off the coma. Follow that up with comet, more observations of comet Ison or HNC. You put in a model, and again, we subtracted the model from the actual observations, so residual. We are now learning more about the chemistry and physics that's going on in the comas. HCN really and methanol comes out in a spherically symmetric outflow. HNC is enhanced in the outer coma along with H2CO. HNC is probably coming from these collimated outflows, probably from the the photo processing of HCN. H2CO, the formaldehyde, we really can't figure out what its parent source is, but methanol is a good proxy, probably, because as methanol comes out of the coma, and the solar system, and radiation field hits it, it kind of photodissociates the methanol into formaldehyde. So that's what we think is going on in the outer coma, to get enhanced abundance of formaldehyde in the outer coma. And I see there is a question in the chat. Before I take the question, going back again to Paul's question about what do we get from the kinematics? We know something about the velocity distribution. We can now do this observation of methanol, but we don't have to integrate for days and days to try to detect it. We can now get the morphology and emission of molecules coming off the coma on minutes timescales. We could actually look at how the methanol is coming off the comet in about 10-minute timescales by looking at every execution inside of the ALMA set of observations. And you can see that, while these are hour averages, you can see that the line profile is changing over these hour averages, showing that there's probably jets and things that are rotating inside the comet. And then in this paper, we actually break it down even further, not on hour timescales, but on 10-minute timescales, to actually show the difference of the line profiles over the course of one set of observations. And if that wasn't enough, you could do this on moons in the solar system. And here we just looked at all the large cyanides in the atmosphere of Titan. We looked at HC3N, CH3CN, vinyl cyanide, and ethyl cyanide, we'll just call them that, but different cyanides. And you can say, well, they all have nitrogen in it. And again, if you just look at a single dish telescope, you point it at Titan, you collect all the radiation, you say, okay, all those molecules are there. But it's clearly showing that the different cyanides are showing up at different poles at the same set of observations. This is telling us something about the photochemistry that's going on in the atmosphere of Titan and how it's being mixed into at higher latitudes and lower latitudes, and also at higher altitudes inside of the Titan atmosphere. So these sets of observations are really opening up a whole new way to look at chemistry in these different types of sources, and it's giving us a better way to understand what chemistry is taking place by looking at the chemical maps. Now, before I go on to the last bit of my talk, any questions?
I think you should probably wrap up
Yep.
and take questions immediately after.
Okay, then I have just a couple more slides here about what are the limits to molecular complexity. Okay, so how big a molecule can we actually find? Well, molecules discoveries are stalling with ALMA. There's a lot of line confusion. There's a huge density of lines that we see, and it's really not giving us a lot of new information. But lower frequency observations are cleaning up, and the proposal for the GBT was basically very forward-looking when it said that these large molecules are going to have very strong transitions at the radio part of the spectrum, centimeter waves. And we're cleaning up. New molecule detections are happening at a tremendous pace, but they're happening at lower frequencies in these cold sources. This is the detection of what benzonitrile from Brett McGuire's work that he did, showing this was really the first proxy of benzene in the interstellar medium. And in addition to that, using new techniques and new processes of match filtering and line averaging, we're actually finding now precursors to PAHs. So this is now being able to be done at lower frequencies. We're finding very large molecules in these sources. With that being said, though, we're still no closer to understanding how these molecules are formed. We need chemical maps. We need, and what we want to do here, interpreting these chemical maps. What kind of data do we need? We need the morphology of these distributions. We need a large amount of spectrum. We look at different isomeric families. We have to understand, all these different isomeric families and where and how these molecules unform. And the detections are just as important as non-detections. And my last comment here is we have to move beyond what we call epicycles to chemical models. This is what I mean. You have a chemical model, it's sitting there, it's doing its thing. I find a new molecule in space. Okay, they go back and they say, oh, I could form that molecule by adding something to the code. Now I can form that molecule. The codes are not predictive. And this is a problem. I want to be able to run a chemical model like I run a physical model, general relativity or special relativity, and say, this is what you should see. You run a chemical model and say, hey, not only are these species there, I could produce those in this abundance, but I could also predict 5 others that you should see as well. And one significant advantage to simplicity is that it focus that it gives us. So instead of adding epicycle after epicycle after epicycle after epicycle onto these chemical models, maybe it's the time to just stop, rethink exactly what we're doing based on all the new information that we have from all these new facilities. So this is what I challenge the group here. I want a global formation pathway for a chemical family, whether it's an acid, a cyanide, an aldehyde, that is consistent with the spectroscopic detections, morphological detections, in any kind of astronomical environment. And I have absolutely no idea how to do this, but that's why you guys are much smarter than me and you can do it. And I leave you with that a quote from Lou, that formaldehyde was the first polyatomic molecule that was ever found in space. And this discovery revealed a vast amount of gas and dust that is found between the stars and really started the exciting branch of chemistry known as astrochemistry. I want to thank Lou, the University of Illinois, for starting me on this journey back so many years ago now. I want to thank my graduate students, postdocs, everyone I've worked with for continuing to work with me to get excited about this work. And thank you everyone for your attention. And I know that I've got 1 more minute, and hopefully I answered your questions during the talk. But thank you again for your attention and for having me present at this, at the 100 years of astronomy at the University of Illinois.
Thanks very much, Tony. And we do have a little bit of time. We could take a couple questions. Yeah, Leslie.
Hey, Tony, thanks. Glycine, I'm particularly interested in why are we not detecting glycine, especially with ALMA, and what do we need to do to detect it in comets, since we do actually have some measurements of comets in our own solar system?
Glycine is probably there, just not at an abundance that we could actually detect right now. That is our working understanding of this type of molecule. As you get to glycine, you have different conformers, and the different conformers are just how the molecules are arranged, and they're arranged in a certain way that they're all very close in energy levels. And so you have all this energy distributed over all of these transitions, over all of these different conformers, and that's just making the actual intensity of any particular line very, very, very weak. And so it's probably there at an abundance that we just can't detect right now. We may need NGVLA or some other of these facilities to do it. Now, the techniques I talked about here that we use to detect some of these larger PAH molecules, it's a very novel technique, but it only can really be used right now in sources that are very clean spectrum, that don't have a lot of overlap with other particular molecules, or that have this line force that we see in Orion. So, if we could somehow use this technique on some of these very complex sources of molecular emission that we see in some of these hot core regions, we may be able to detect it that way. Or we have to wait for NGVLA, look at it at lower frequencies where there's much less line confusion. And then one of the things that we been discovering over the course of the last several years is that all these these large molecules all have maser transitions down at low frequencies. So some detections are only seen because of their maser action. So maybe glycine one of the particular transitions could be a maser transition that we may be lucky enough to detect. But that's kind of where we're at with glycine and why we can't see it right now.
Okay, thanks.
Brian. You there, Brian?
Hey, Tony, thanks for your talk. That was great. So forgive me, I have some science questions, but I just have to say this. So you mentioned Lou and his great science, but everyone has a Lou story, and I'm sure you have many Lou stories aside from science. But maybe is there a brief one that you could repeat for this audience?
Yes, a Lou story. Okay, a Lou story, a very brief one, is Lou Snyder, Mike Hollis, Phil Jewell, Frank Lovis, and I were in the elevator of the GBT. And we were talking, we were getting all these new molecular detections back in 2004, 2005. And we were not fighting amongst ourselves and say, but discussing about the competition in astrochemistry and how this person's not going to like it and how that person's not going to like this detection because we only have 3 lines, et cetera, et cetera. And I'm brand new, right? You have these are the giants of astrochemistry. I'm in the elevator with, and Lou looks at me and he goes, just remember, all of my enemies are now all of your enemies. So just remember that. And I'm like, thanks, but there's 5 of you and 1 of me. So, okay. So I try not to make any more enemies in astrochemistry, but I thought that was hilarious that he's like, all the enemies are my enemies, now your enemies. Thanks, Lou. Appreciate it.
That's great. Thanks, Tony. That's a great Lou quote.
Hi, thanks,
Hey,
Tony.
Rachel.
So in one of your last slides, you mentioned that there's an open question about whether the distribution of molecules traces chemistry or just abundance. So what would it take to tell the difference between those 2 scenarios?
Right. Okay. Great question. And the answer comes to this part of, we need a lot of transitions to make a chemical map, because, if you say you're just looking at a 300 Kelvin upper state energy level line, well, that may be with a high critical density. When you map that line in a particular source, you may only then be looking at high temperature gas at a high density, right? Or let's say you look at methanol. Well, methanol is highly abundant. It seems to be everywhere. So whatever transition of a molecule like methanol you look at in space, it's going to be just everywhere. Maybe we're just plotting, well, just because the molecule is abundant, it's everywhere. Maybe we're just plotting abundance. So the more chemical maps we can make of molecules, where we could really try to tease out, okay, this is a high energy transition or a high critical density transition. We can tease out all that information and make these ensemble chemical maps like CC has done with methyl formate and acetic acid that really shows all the transitions of molecules average, on top of each other, and really gives us a good chemical image of the source. That's how we're going to start disentangling chemistry from physics. So when you look at different morphologies, we look at where molecules are at in different sources. We have to make sure that we're not answering this question of, well, is this high temperature region, low temperature? Is this on a PDR or not on a PDR? If you take all that physics out of it, and we're now look at really just the distribution of one molecule with all the transitions and another molecule with all the transitions, now we can start answering questions about differences in morphology leading to understandings in chemistry, not just different physical conditions.
Thanks.
So I don't see any other hands, but I do have one question of my own, and that has to do with your last statement there about how we should change the approach to chemical modeling. Yeah. So I don't even play an astrochemist on TV, so I, probably this is a naive question, but my understanding was that a lot of these molecules, obviously apart from common ones like methanol, for example, are difficult or impossible to form under terrestrial conditions. And so what would it take to figure out reaction rates and, basically to be able to do this, given especially the fact that these are probably not in chemical equilibrium and not in LTE necessarily?
Well, for some of these things that we're talking about, yes, that could be the case. But, for some of the acids that we see, right, formic acid, acetic acid, glycine, those are relatively easy. You could find them underneath your sink, right? Pick up a bottle of vinegar, that's acetic acid, right? The question is, forming them under interstellar conditions, that's the big question. And you go into any organic chemist lab and say, yeah, I want to form large molecule like acetone or methyl formate or all this, or they'll just say, okay, well, that's fine. You can do it in this, add this chemical, that chemical, this reaction. But I'm like, no, I want to do it at, 5 Kelvin at 1 particle per cubic centimeter, or at, they say, get out of my office. It's ridiculous. I don't know what's going to take, Paul, but what I can tell you is that, when you start looking at, from a history of astronomy point of view, it takes someone looking at the problem from a novel way, in a unique way, in order to make the big change, right? And just the epicycle example is just one of them, but that really changed the way that we think about how to do this. We are very terrestrial chemistry, kind of, thinking right now. They're not, Newton's laws are not applicable at the speed of light. Newton's laws are not applicable in quantum theory, right? It takes a brand new way to think about it. You can't take a Newton law and just keep kind of pigeonholing it into, quantum theory. It just doesn't work. You got to think about a new way to do it. And I don't know how to do this, but this is what I'm asking is we keep adding these reactions. They say, oh yeah, I could form that. Oh, I could form that. But yet there's not been one chemical model that has been predictive. And that's, and that I could say, to what you could, if you find these 3 aldehydes or these 2 acids, this is the next one in the chain, because I understand the chemistry well enough to say that, then I should form this molecule at this probability, like I'm 99% confident that this molecule is going to form. Now, there's a great new paper out by Kelvin Lee and his colleagues that look at the structural similarity between molecules and looks at maybe what molecules should go after next from a machine learning point of view, which is a fantastic piece of work. But from understanding chemistry, do we understand chemistry well enough to say that I understand chemistry enough to find this molecule in this source under these physical conditions, and then actually go and test it and find it?
Mm-hmm.
I don't know how to get there, but that's really what we, and again, challenging the group, the young people in the group to think about, hey, how can we actually do that?
Okay, thank you, Tony.
I have a question if there's time.
Sure. Okay. Well, those who wish to leave should feel free to do so. But we can keep Tony a little bit longer if he's willing.
Sure.
If there are more questions. Go ahead, Tony.
Is it okay to ask?
Yeah.
Yes.
Tony, it's good to see you. I enjoyed your talk very, very much.
Thank you.
As you may remember, back in the early 1990s, a then student of mine, Glenn Sayerleg, and I showed that the dynamics of each one of these cores or fragments, whatever one might call them, actually affects the chemistry. In particular, small grains, because they are charged at the densities of interest, are better attached to magnetic field lines than large grains. And because all these, or most of these molecules form on surfaces of grains, that should really affect and have predictive value if one were to abandon the static equilibrium abundances way one calculates molecular abundances and introduce the dynamics. I have not seen any group following up on this. Are you aware that anybody is doing that? We demonstrated through numerical simulations that that's unavoidable. Is anybody following up?
Okay, I think the answer to your question, no, I haven't seen anything, but I was only catching about 1 out of every 3 words. So the connection is not that great. I'm sorry, but that's a great thing to follow up on. I don't think anyone is doing it. And I can also tell you that when we were thinking about this type of chemistry back in the 90s, like we were talking about, and early 2000s, grain chemistry was going to solve all of our problems. Everything was formed on a grain surface. And gas phase chemistry could not produce these molecules. It takes 20 years, but pretty soon you start to come back to some molecules that we're finding, and the molecule we detected in about 10 years ago cannot be formed on a grain surface. The only way to really form in any type of abundance is through gas phase reactions. So we have to start going back and looking at not only a grain surface model for some of these molecules, but gas grain models, or even just pure gas phase chemistry in order to produce these things. But you're right. Some of these, I think I actually remember that paper from way back when. And I say way back when, it's like the 90s are now 30 years ago. It's amazing. But no, I don't think anyone's following up on that. But this is the kind of different thinking that we have to really need, because existing models are not predictive and they're not answering the big questions that we need. So, and again, Telemachos, I'm sorry, I only heard about 1 out of 3 of your words, but if you want to follow up with me afterwards, send me an email. I'll be happy to talk to you more about it.
That's okay. You answered the gist of my question. Thank you.
Yeah. Yep.
I think this is a little bit related to the question I asked too, because in order to calculate chemical dynamics like that, you need to know those reaction rates.
Mm-hmm. They're very different, and they're very expensive to either calculate or measure. Yeah.
Yeah.
And there's not a whole lot of folks in the lab that can spend time or money to do those kind of things.
Right.
Purely for understanding interstellar chemistry, right?
Well, we can't necessarily achieve in the lab the same.
Yeah, that's true too. Mm-hmm.
Brian, you had a couple of questions.
Oh yeah, so Tony, great to see you. Great talk. So two naive questions, which, as you know, are the only kind I ask. So for the comets, you were mentioning that you got all this interesting time domain information, and you saw how the lines change with time. Is it over, like, say, the span of a PhD thesis? If you look at Orion or someplace like that, is there any hope that you would actually see time variation? That may be a stupid question. I have no idea.
No, there are some sources that you can, and they talk about these like bullets that are coming out of the Orion Nebula and stuff like that. So there are, we are now starting to see, time variability on some of these, in some of these sources. And if you look at some of the more recent work done on methanol and formaldehyde masers in some sources, there's a worldwide consortium that is constantly observing sources in the sky, waiting for masers to go off. And especially in NGC 6334I, there was a maser that happened several years ago. They could actually see huge brightenings of particular transitions of lines in these sources. That gives us looking at trying to understand what's going on physically that happened in order to pump that maser to such to several orders of magnitude brightness. So there are things going on in interstellar clouds that we are now monitoring, and we can monitor on timescales of months or years, that are changing the molecular composition of some of these sources. The maser one is actually really cool because it blew up, and we've had follow-up observations with ALMA on all these different types of sources, and it was a very interesting where the masers are actually located with respect to like the outflows and stuff of these sources.
Oh, that's neat. I didn't know that. They're very cool. So the other thing is, so my it's not really a Lou story. It's a Doug Friedel story. I think it was on Doug's prelim or something. And I was like a new professor. I didn't know anything about anything. And he showed one of the spectra like you did. And I looked at all those lines and I saw all those U's. Oh my God, you discovered uranium. That's so cool. And he's like, dude.
Yeah, unidentified.
So when you showed the Orion, the ALMA Orion spectrum, all like
yes.
the thicket, are those all basically unidentified? Or is it it's unambiguous what they are?
The numbers haven't changed. About 50% of all the lines that we detect in space are unidentified. That's consistent from 1980s through now. And for some of these sources like Orion or Galactic Center, we can identify about 50% of the lines. For some of those more simple sources, protostellar cores, dark clouds, then we could identify a much higher fraction. But as we go down to this type of level, every bump and wiggle down here almost becomes, where is continuum? And it's,
right.
We talk about the continuum of Orion. Well, there isn't really any continuum in Orion. It's mostly molecular emission. Maybe up to 50% of the emission that you could identify as continuum emission of Orion is actually coming from molecular emission at a very, very low level. So it's, and even with all the spectroscopy you have, with all the new molecule detections, all the isotope logs, all the 13 carbons, the deuteriums, everything, we still only identify about 50% of the lines that we see.
And are most of them, like as Paul was mentioning, you can't access them in the lab?
Oh no. I mean, some of these we don't know what these lines are coming from. We have no idea what molecule these lines are coming from. So whether we could synthesize it in the lab is we first got to get an understanding of what it is to try to form it. And that's another Lou story, is the detection of exogen, right? So Lou discovered a line in space about 88 gigahertz, and they knew it probably was some carbon oxygen molecule, but they didn't actually couldn't characterize it because it wasn't characterized in the lab yet. So they claimed the detection of exogen, and it turned out to be HCl plus. So that's the original detection story of that. You could also look up the original detection paper of ethanol, and I think they quote a proof of the interstellar medium in ethanol.
That's great.
Yep. So that's what I'm saying. Let's have some fun with this, right? Astrochemistry is fun, man. It's fun talking about this. Paul, you didn't actually, my entire thesis, right, was on, complex interstellar molecules, but it was on acetic acid and urea. My entire thesis at the University of Illinois was on piss and vinegar.
I was waiting for you to say that, Tony.
Yeah. So, I mean, if you can't have fun with astrochemistry, you're doing something wrong.
Well, with that, I think that's a great place
We're done, right?
to stop. Thanks so much, Tony. And this was really, really interesting talk. And I'm just waiting for the next comet of the century and seeing what you can do with ALMA on that.
Yeah, that's there's that big one coming by that's already showing activity at 10 AU. Can't remember what its name is, but yeah, we already have ALMA on it.
Awesome.
We're trying to see it.
So that's in the spring, I think, right? It's supposed to reach perihelion. So great. Okay, well, thanks everybody. And Leslie, if you can go and stop recording and send me the recording, that'd be great. Thank you.
Yep. Thanks, Tony.
All right, take care, everyone. Good to see you.